Welcome to the deep dive. Okay, today we are jumping straight into a really exciting architecture paper, scaling latent reasoning via looped language models. This is the one introducing the Ouro model family.
Yeah, this is a big one, especially if you're focused on efficiency. It really challenges that core assumption, that LLMs have to scale just by adding more parameters.
Absolutely. All right, let's hit the main points right off the bat for that quick summary. First key insight, parameter efficiency. Ouro brings in these looped language models, LoopLMs.
That's right, LoopLMs, and they integrate this iterative sort of internal computation during pre-training. We're talking a massive scale here, 7.7 trillion tokens.
Okay, and that intense pre-training gives you insight number two, performance. These models are small but mighty. Ouro 1.4 billion, 2.6 billion parameters. They're matching or even beating standard transformers up to 4 billion, even 8 billion parameters.
Yeah, beating them. It's a genuine 2 to 3 times efficiency jump. Really quite remarkable.
It is staggering, which leads to the third point, how they do it. It's not about cramming more raw knowledge in. They actually tested this, and storage capacity is still around 2 bits per parameter, same as usual.
Right. So the magic isn't storage, it's superior knowledge manipulation. It's about how the model processes information internally.
Gotcha. And the fourth key bit is the mechanism enabling this, an adaptive exit gate. It's trained with a specific entropy-regularized objective. And this is important, using a uniform prior.
Exactly. That uniform prior lets the model dynamically choose how many internal thinking steps it needs for any given input. More complexity, more steps. Simple stuff, quicker exit.
Okay, fantastic summary. Let's dig deeper because, wow, this feels like a potential shift. For years, the main scaling knob has just been make it bigger, more parameters.
Right. Billions, then tens of billions, hundreds, and we just hit a wall. The infrastructure costs are enormous. Latency becomes a killer for anything real time. And frankly, it limits who can even use these things.
Yeah, accessibility is a huge issue. So parameter efficiency became the holy grail, getting more bang for your buck, basically.
We needed ways to get more capability without just endlessly scaling up the parameter count.
So before this, what were the options? Well, you could try scaling the training data.
Which works, to a point. But we're starting to bump up against the limits of high-quality data out there. Data scarcity is becoming a real bottleneck.
Okay, so data scaling has its limits. The other main path was inference time compute tricks, like chain of thought, SOTA.
Right, CoT is clever. It lets the model show its work, generate intermediate reasoning steps, but the downside is obvious. It makes the output sequence much longer.
Which slows down inference time considerably.
Exactly. You're trading off speed for that explicit reasoning path. And it also puts a massive strain on your KV cache memory, which grows with the sequence length.
So CoT helps with reasoning quality, but hurts latency and memory. We needed something else, something architectural.
Which brings us right back to LoopLM. This is the third pathway they're proposing. It's architectural innovation.
And the core idea is decoupling parameter count from computational depth.
Precisely. Instead of needing more parameters for deeper thought, you reuse the same parameters multiple times. You apply a shared block recursively.
Ah, I see. So the model can think for longer, iterate internally without physically getting bigger.
Exactly. And the beauty of this LoopLM structure is that it inherently supports adaptive computation, that learned exit mechanism we mentioned earlier.
Yeah.
It lets the model bail out early for simple inputs. Just one loop might be enough. But for harder problems, it can automatically decide to run more loops, allocate more compute without the user needing to specify anything.
Okay, that's clever. Let's get into the weeds of that architecture then. How does it actually work?
So think of a standard transformer. It's a stack of distinct layers, right? Layer 1, layer 2, layer 3, each with its own parameters. LoopLM throws that out. It takes a single shared transformer block, just one set of parameters, and applies it over and over again, recurrently. Each pass, each iteration refines the internal state, the hidden representation dollar.
So each loop is like a step of internal reasoning, refining the thought.
That's exactly how they frame it. Steps of latent reasoning. It's computation happening internally on the hidden states before generating the next output token.
And making this work well requires some smart training. You mentioned 2 stages. Stage I is about that entropy objective.
Right. Stage 1's goal is to get the model used to this looping idea and explore different depths. The objective is basically minimizing the prediction error, average across all possible exit steps up to the maximum they set, which was 2 max for during pre-training.
Okay, minimize error.
Yeah.
But there's a penalty term too, the entropy regularization.
Yes, beta checked at HQ5. That penalty encourages the model's exit probability distribution to be spread out rather than sharply peaked. It forces the model to actually try stopping at step 1, step 2, step 3, and step 4 during training.
So it learns the value of different computational depths.
Yeah.
And you highlighted the uniform prior as being key here, different from something like PonderNet.
Hugely important difference. Many adaptive methods use a geometric prior. That inherently pushes the model to exit early. It basically says shorter computation is better.
Which might be okay for some things, but not for really hard problems.
Exactly. Ouro uses a uniform prior. It assigns equal probability to exiting at any step. There's no built-in bias towards shallowness. It tells the model, look, figure out from the data itself whether you need 1 step or 4 steps. All depths are equally likely a priori.
That seems much more flexible. It avoids baking in a bias that could limit its reasoning power. Okay, so that's stage 1. What about stage 2, the focused gate training?
Stage 2 is about fine-tuning that exit gate for optimal efficiency. Instead of just the abstract entropy penalty, they train the gate based on concrete progress. Did the last loop actually help much?
How do they quantify help?
They calculate the loss improvement, LTI and a tech stack stop. Basically, how much did the prediction loss decrease because of that last step of reasoning?
Ah, okay. So it learns to stop if the improvement is tiny.
Precisely. They train it to avoid 2 failure modes. Underthinking, stopping too early when the improvement was actually large, meaning more thinking would likely have helped significantly.
And the other one?
Overthinking, continuing to loop when the improvement is negligible, below a small threshold tau, which they set empirically to 0.005, it learns to recognize diminishing returns.
So it really fine-tunes that stopping decision based on measured progress.
Right.
Very neat. And they train this on a huge data set.
Massive. 7.7 trillion tokens. They use sophisticated pipeline techniques too, like curriculum tuning and annealing, long context training up to 64K, even mixing in some instruction tuning mid-training.
And the key training parameter was that max recurrent depth, T4 tolerance.
Yeah, T4 tolerance was the setting during pre-training. And the results, well, they speak for themselves.
Let's talk results then. That 2-3x parameter efficiency claim is bold. How does it hold up?
It holds up incredibly well. Our O1.4b, when run with 4 loops R4, consistently matches the performance of 4 billion parameter baselines, like Qwen3 base.
Okay, 1.4b matching 4b. What about the bigger Ouro?
Ouro 2.6b R4 actually outperforms 8 billion parameter models, like the 8b Qwen3 base, on many benchmarks.
Wow. Any specific examples that stand out?
Oh, yeah. Look at math reasoning, which is notoriously hard. Ouro 1.4b hits almost 79 on GSM-8K and over 82 on MATS 500. The Qwen3 4b baseline, it gets about 73 and just under 60, respectively.
That's a massive gap on MATS 500, almost 23 points better from a model less than half the size.
It really shows the advantage for complex reasoning tasks, and they push this even further with fine-tuned versions called Ouro Thinking.
Right, the SFT models.
Yeah, the Ouro 2.6b Thinking R4 model manages to match or beat the Qwen3 8b on really tough stuff, like Olympiad Bench and Beyond Aim.
And does the performance scale nicely with the number of loops, T?
It does, and it confirms the iterative idea. Performance at T1, just 1 pass, is consistently quite low.
Yeah.
The model needs those recurrent steps.
This is not just a slightly better feed-forward model.
Definitely not. It relies on the iteration. And interestingly, performance generally peaks right around T4, which is the maximum depth it saw during pre-training.
That makes sense. Okay, so we know it works. We see the benchmarks. But why? Why does looping over the same parameters boost reasoning without adding parameters? Is it storing more knowledge somehow, or is it purely about the process?
That's the million-dollar question, right? And they tackled it head-on with some really clever synthetic tasks. First, they tested raw knowledge storage capacity using something called the capo task.
Okay, what did capo show?
Basically, looping does not increase the raw storage. Whether you loop or not, the models hold about 2 bits of information per parameter. That seems pretty fixed. So parameter count still dictates your raw memory.
Right. So the brain size didn't increase. The way the brain works must be different.
Exactly. It's not storage, it's manipulation. They tested this with other tasks, mono, which involves modular arithmetic, and multi-hop question answering. These require chaining steps together, composing knowledge.
And how did LoopLMs do there?
They significantly outperformed standard transformers at the same size. The looped architecture just seems to have a much better inductive bias for using knowledge flexibly, for combining pieces of information, for searching through what it knows.
That aligns with their theoretical argument too, right? Connecting it to things like graph reachability.
Yeah, they make the case that LoopLM is a form of parallelizable latent reasoning. It can solve certain problems, like finding if two nodes in a knowledge graph are connected, much more efficiently in terms of sequential steps compared to, say, HOTD, which unfolds everything sequentially in the output.
So fewer sequential steps, potentially faster deep searches within its own knowledge.
Essentially, yes. It's a more efficient way to structure deep compositional thought.
Okay, let's pivot to practicalities. Deployment. That adaptive exit gate, the Q exit, how well does it balance accuracy and compute in practice?
It works really well. The gate trained in stage 2, the one focused on loss improvement, gives the best trade-off. It hits the best Pareto frontier curve for accuracy versus computational cost on benchmarks like MMLU.
Better than just using the entropy penalty from stage I.
Yeah, about 2-3% better accuracy for a given compute budget. That specialized training really pays off. Though, interestingly, they found that just looking at how much the hidden state changes between steps in the L2 distance is actually a surprisingly decent proxy for convergence. Not quite as good as the explicitly trained gate, but not bad.
A useful heuristic, maybe. Now, the elephant in the room for recurrent models, memory, especially the KV cache during decoding. You said naive LoopLM could be 4x worse.
Yeah, if you store the full KV cache for every single internal loop, $4,000, and then also for every token you generate, the memory overhead balloons, that would make it impractical to deploy.
So how did they fix it? That sounds like a deal breaker otherwise.
It's a really neat optimization. They realized that during token generation, you probably don't need the exact intermediate KV cache from every single loop.
Okay, so what do you use instead?
They tried two things that worked well. Either just reusing the KV cache from the very last loop, step T4, or using an average of the KV caches across all the loops.
Like summarizing the internal thought process for the next step.
Kind of, yeah. And the amazing thing is this cuts the KV cache memory overhead by 4x back down to standard levels, but with almost no performance hit. Like less than 0.3 points drop on GSM 8K.
That's huge. That makes it actually deployable.
Yeah.
Okay, memory solved. What about model behavior? Faithfulness is a big one. Does LoopLM just rationalize an answer it decided early on, like some people suspect CoT does?
It seems not. They provide compelling evidence for causal faithfulness. The reasoning process appears to genuinely influence the final answer rather than just justifying a pre-existing conclusion.
How do they show that?
They used an agreement matrix. They looked at whether the model's prediction after, say, loop 3 agreed with its prediction after loop 4 on the same input.
Did they agree?
Often they didn't. For example, the agreement between step 3 and step 4 was only around 36% on one task. This means the model was genuinely refining its answer, changing its mind as it looped more. The final decision emerged from the process.
That's really cool. It suggests the internal steps are actually doing meaningful work.
Okay, last major finding, and maybe the most surprising, safety alignment.
This one is fascinating. They tested the models on the Hexic-CHI benchmark, which measures harmfulness. Now remember, task performance peaks around T4 and then might degrade if you push it further.
Right, because it wasn't trained for T5, T6, etc.
Exactly. But guess what happened to the harmfulness scores as they increased T from 1 up to 8?
Aha. They got worse?
No, they got better. The harmfulness scores decreased consistently as the number of loops increased. The model became safer with more iteration.
Wait, seriously? Even in the extrapolated regime, T5 to T8, where task accuracy was dropping?
Yes. Even when the model was arguably getting worse the task, it was getting better at safety alignment. More loops led to less harmful outputs.
How is that possible?
Their PCA analysis suggests that with more iterative steps, the internal representations of benign versus harmful prompts become more clearly separated in the hidden state space. The looping seems to enforce some kind of consistency or control. That is wild and potentially very important. So wrapping this all up, what's the big picture here?
Ouro really makes a strong case for iterative latent computation looping as a viable, important third scaling axis for LLMs. It's not just about parameters or data anymore.
It's about efficiently manipulating the knowledge you already have within a fixed parameter budget.
Exactly. You get smaller models, better reasoning, deployable efficiency thanks to the KV cache fix, and seemingly more faithful and controllable behavior.
Which brings us to our final provocative thought for you, the listener. We just heard that task performance can degrade when you extrapolate loops beyond the training limit, like T5 to T8. but safety alignment actually improves in that same regime.
Yeah, that divergence is key.
So could we imagine future LLMs intentionally designed to leverage this?
Huh.
Maybe you run the model to T4 for optimal task performance, but for safety checks. Or in highly sensitive applications, you push it into that extrapolated, computationally more expensive regime, T5+. Not for better answers, but purely for enhanced control, consistency, and safety.
It poses a really interesting question about resource allocation, doesn't it? Should we sometimes optimize compute purely for safety and control, even if it means sacrificing a tiny bit of task accuracy in those specific moments? It suggests this iterative architecture might offer unique knobs for just that, something to think about.